Well, we're going to start with the last talk of this long year of the International Year of Statistics. And as we said in Mexico, vamos a cerrar con broche de oro, meaning that we have a great speaker, one of the most important statisticians nowadays, and which is Emmanuel Candes. Emmanuel Candes is professor in the University of Stanford, and he did his undergraduate studies in École Polytechnique in France, and he obtained his PhD in Stanford under the supervision of David Donoho. And amongst his awards, so we have that he got jointly with Terence Tao the George Poljar Prize in 2010, and recently the College Prize in 2011. So his works in nonlinear approximation theory had a huge impact in image processing and multi-scale analysis. And in 2004, Emmanuel Candes, jointly with Terence Tao, they kick off the field of compressed sensing. So I'm glad to present Emmanuel Candes today, that he will speak about robust principal component analysis.
Thank you very much. Thanks for a very kind introduction. It's a really great pleasure for me to be here, both to celebrate the International Year of Statistics and also to be in beautiful Guanajuato, which I think is really a spectacular place. So today, instead of giving you a broad survey of stats, I'm just going to tell you a little bit about some recent work we've done in the area of robust principal component analysis. And before I get started, first of all, I'd like to encourage you to interrupt me anytime something is not clear, to make it a bit lively. And also, I'd like to acknowledge that this is joint work with collaborators, namely Xiaodong Li from Stanford University, my former student, Emma and John Wright, who are wonderful researchers in computer vision, Emma being at Microsoft Research in Beijing, and John Wright at the University of Columbia. Okay, so I want to kind of introduce a very simple problem, a problem that is very simply stated, and this is what we're going to call the separation problem. And so in this problem, it's very, very simply stated. As a statistician, I get to see an observed matrix, which we're going to call M. It's a data matrix. And I'm going to posit that this matrix is a superposition of two matrices. One, which we're going to call L naught, which has low rank. So this is going to be this guy, which I pictorially represent like this. So because it has low rank, it's a matrix with correlated columns, and a sparse matrix, which is not observed. I just get to see their sum. And the problem is, can we recover the two components, the low rank component and the sparse component, accurately? And of course, this problem seems extremely daunting. It's a bit like, I write two numbers A and B in my hands, and I show you their sum, and you see 3, and I ask you what is A and what is B, and it looks a bit delicate. But I claim that if we knew how to do this, then it would really have enormous practical consequences. And let me just introduce you to why I think this problem is important. Okay, so I think we all know what is principal component analysis. In principal component, I mean, this is a stats department, so kind of this is a most widely taught subject in applied multivariate statistics. We've got a data matrix M, which is a superposition typically in classical PCA of a low-rank matrix and a perturbation. And so what we think about when we write a model like this is we say, well, the columns of M, so I've got M, my matrix M, and the columns are data points, right? And so when I plot these data points, they may be in high-dimensional space, but they may be very well localized around a low-dimensional structure. And so if I plot these points as in n-dimensional space, what I'm going to have is that, well, they could be well distributed around a low-dimensional structure, not exactly on the low-dimensional structure. If they were exactly on the low-dimensional structure, we would have exact low rank, but they're distributed about a low-dimensional structure. That's why we have a perturbation. Right? And so when we do dimensionality reduction, Well, what do we do? What is a method of principal component analysis is give me a collection of points, columns of a data matrix, try to find the best low-rank approximation of this matrix M. Okay, so this is the method of principal components introduced by Schmidt and Hotelling. And, well, the computational answer, I think we all know what this is. I take my data matrix M, I write down its singular value decomposition, okay, use sigma V transpose, and what I do, the recovered low-dimensional structure is I just truncate this singular value decomposition as to keep only the largest singular vectors, and that's basically how we do dimensional reduction, right? So this is capturing the plane with maximum variance. Is everybody with me, or? Okay, great. Absolutely. Well, that's PCA. That's kind of what we all know. Okay. Now, one thing that, so we teach PCA to everyone. And one thing we don't discuss so much, and I think it's a bit unfortunate, especially in this big data world, is that PCA is extremely sensitive to outliers. And here's what I mean by this. Suppose that I've got, and I can only draw in the plane, so this is really in the plane. Suppose that the points lie along a low-dimensional structure. Here is a single line. And I fit PCA, and I find the line with maximum variance. Well, we're going to find this line, and everything is well. Suppose, however, that in the data collection, there was one data point, one entry in this data matrix that was incorrectly recorded. For example, suppose that this blue point, I got its x value right, but its y value, I got it wrong. So that now it's there. Like maybe because the sensor failed. Or like, you know, the people who enter the data in the computer, you know, they press the wrong key. Then what I've got is all the points are here, this data point is here, I fit the principal component and I get this line, which has nothing to do with the line of first variation. And so what we see here is that with just one single corrected entry in the data matrix, the thing completely breaks down. And it's a bit troublesome because in this kind of big data world in which we live, you know, we deal with large collection of images, videos, web data, user data, and we cannot assume that data is clean. Right? We will have incorrect entries in huge data tables. And so the problem is, if we start to apply PCA to reduce dimension on data matrices that have been corrupted, then we're going to get garbage. And so the point is that gross errors, of course, frequently occur in many, many applications. So because this is joint work with computer vision people, you're going to see a lot of applications in the area of computer vision at the end of the talk. And so in computer vision, you may want to kind of recognize faces of people. So that is a very kind of intensely studied subject in computer vision. So you've got various faces of people, and you would like to have a system that automatically recognizes people. And so there is a little theory that says that if I have a picture of the same individual under varying illumination conditions, then when I look at the data in pixel space, it spans a very low dimensional structure. So it's kind of, there's a theory that would say that, you know, when I look at the data of the same individual under varying illumination condition, you're looking at a 9-dimensional space, essentially. So very, very low dimensional. Okay, but the problem is, well, this is occurring under ideal conditions, but when you kind of want to deploy, and that's why face recognition is a hard subject, is most often we're not under ideal conditions. And so we're going to see pictures that look like this. So we may have occlusions. We may have occlusion because one day I'm going to show without my glasses, and the next day I'm going to show, and I'm still the same person. Right? But if you were to take cues from glasses, you'd kind of be in big trouble. Right? And so when you retrieve image data over the internet, you know, you have lots of occlusions, lots of missing pixels, and so on. And so these computer scientists, they want to kind of reduce dimension, but classical method will completely break down because of gross errors of this type, occlusions typically. So in web data analysis, you know, for example, are you familiar with the Netflix problem? Yes? Okay. Well, when you deal with web data, when you deal with data that have been entered by users, then you cannot ignore the fact that people can tamper with data and will corrupt them on purpose. When you have in bioinformatics, we can have sensors that fail, and for all these reasons, we cannot assume that we have a clean database, and so it's very, very important before we apply dimensionality reduction to kind of clean it up in some ways, or to make PCA robust. And there's been a large literature in the literature of statistics that deals with such things, but what I'll present today has nothing to do with what has been done before. Okay. All right, so this is kind of the motivation. The motivation for me really is this, is that I want to do PCA, but I cannot ignore the fact that the fraction of the entries in my data matrix may have been corrupted, may have nothing to do with the underlying truth. Now, there are many other applications where this separation into a low rank plus a sparse component might be useful that have nothing to do with robust PCA, and I will just show you one which I think is cute. So again, this is work with my colleague who work in computer vision. And another intensely studied problem in computer vision is that basically if I give you a video sequence, can you separate the foreground from the background? Right? So here you've got a frame of an image taken in an airport, and what you'd like to do is you'd like to have an automated system that essentially recognize what is foreground, what are the people moving about the airport from the background, and automatically extract them to, for example, to track them and so on and so forth. Okay, so the problem is detect any activity in the foreground. Now I claim that this is a problem of a little bit of the type we're studying because, well, so if I have a camera and this camera is looking at this room or like let's say a lobby in an airport, the background is not changing with time. It's not changing very much with time because it's background. That's a definition of background. So if I were to look at, if I have a video sequence, that is I have image 1, image 2, etc. in time, and I were to actually put this image as column of a data matrix, so this is image at time 1, right, this is image at time 2, this is image at time 3, well, the background is really extremely correlated in time. It doesn't really change in time, so it's a low-rank component. And the foreground, as we can see, well, it's going to be a sparse disturbance in this kind of low-rank landscape. And so if somehow I could separate the low-rank component of this data matrix, of this video sequence, from the sparse component, then perhaps I might actually do automated background-foreground separation, which is a bit of a daring proposition. Okay. Here's a Netflix thing, and so who has never heard about the Netflix price? Okay, so the Netflix price, it's something that has excited the machine learning community for like about 6-7 years now. The problem is this: Netflix is a company that rents movies in the United States, and so at the time of the competition, they were renting about 20,000 movies, which we can think as being the columns of a data matrix. And they had about 500,000 users, which we're going to think of as the rows of this data matrix. And sometimes Netflix, well, always, Netflix will ask you whether you like the movie or not. So you're going to have to give it a rating. And so users will give ratings to a few movies. Okay? And out of the 20,000 movies, a typical person will rate about 100. So they have a very sparsely sampled matrix. And what Netflix wants to do is that they want to kind of complete this matrix. They want to infer how you're going to like a movie that you have not yet seen. And for obvious reason. Why would they want to do this? So they can sell you more. Right? So they want to know whether, like, let's say I'm here, whether I'm going to like The Godfather. Right? Because if they're very successful, then I'm going to, I think the goal is very clear. And now there are many, many things like this. This is called a recommender system, and if you can imagine that if you purchase music online or books online, many things are of this form. Okay, so the idea is this, but then what I learned by looking at this Netflix price is that, well, there are users who enter bogus ratings. Like they enter ratings that have nothing to do with their true preferences. And I don't know why they do this, but it occurs. And so what that means is that in this data matrix, there are ratings that are reliable, and there are ratings that are completely unreliable. And here I have a problem which is a bit harder than the one we had before, in the sense that we have lots of missing ratings, and of the few ratings, a fraction are completely unreliable. Yet I would like to kind of recover this whole matrix globally. Now the low rank assumption here makes a lot of sense, because really, how many factors determine anyone's preference for movies? Not a lot. I mean, I don't think in 100-dimensional space, I think. And so, yes, indeed, there is a low-rank model, a factor model lurking behind. The true Netflix ratings matrix we can think about being very well approximated by a low-rank component, of which we see only a few ratings, and of those few ratings we get to see, some are corrupted. And so the problem is, we have a problem which is more ambitious than before, that not only we want to separate the low rank from the sport, but we also want to complete this matrix. Okay, my last example of a separation problem is not my work now, it's the work of Chandrasekharan and all. I think it's very beautiful, and it has to do with graphical models. So before I get there, are there people familiar with graphical models? Or okay, so a few people are familiar with graphical models. So you're given a Gaussian Markov random field, so it's a fancy name for saying that you're given a multivariate Gaussian vector with, say, mean zero and covariance sigma. And people will typically represent such a structure by a graph. And so we have the variables. Let's say here we have 6 variables, and we're going to have a graph, and then we're going to put an edge between 2 variables if they're conditionally dependent given everything else. Okay, so we're going to put an edge between 1 and 3, because this seeing an edge means that x1 and x3, given everybody else, they're still dependent. But I don't see an edge between x1 and x2 because x1 is conditionally independent from x2. Now, if you have a Gaussian random Markov field now, well, what entries, between which pair of variables you get an edge is very simple. What you do is you look at the covariance matrix, you invert it, you get what in statistics we call the precision matrix. And what you see is, like, you look at S inverse. If you see a non-zero entry, you're conditionally dependent. If you see a 0 entry, you're conditionally independent. And so depending on whether you see a 0 or not, you put an edge. Okay. So this is a graphical model. Now, when we go out there and collect variables, we would be really fortunate if we had measured all the variables of interest. Typically, they are what we're going to call hidden variables that have not been measured, latent variables that have not been measured. And so here I have a graphical structure which is going something like this. I have white variables that have not been measured, and then I've got these gray variables that have been measured. Okay, let's say that's a true graphical structure. We see that conditionally, the gray variables are extremely conditionally independent, right? So there's just one edge. But I don't get to see this. All I get to see is this. And the question is, can I actually recover this part of the graph, even though I don't see the white variables? It sounds extraordinarily difficult. Okay, so I have a model with a few observed and a few hidden variables, and so I'm going to split my vector x into the observed part, sub O, and the hidden part, sub H, and jointly it's Gaussian. Okay. So the covariance matrix of the whole process that I cannot observe is going to be the covariance matrix of the observed variable, the covariance matrix between the hidden variables, and the correlations between the observed and hidden variables. And of course, I cannot observe any of this, because I have not observed the hidden variables. And similarly, we can write the precision matrix in essentially the block form, the same block form. Now there is a remarkable relationship called the short complement formula from linear algebra that says that the inverse of this block is equal to this block minus its short complement, which is this, right? So this is a fact of linear algebra. This is a short complement formula that I'm sure you've seen in linear algebra, numerical linear algebra. But this formula is very, very interesting. And this formula is interesting because, well, I see the observed variable, so this is observed. The inverse covariance matrix is observed. This is not observed, this is not observed. But if I have a sparse graphical model, this is sparse. And if there are not too many hidden variables, this is low rank, because the maximum rank of this is a number of missing variables, a number of latent variables. And so I've got a decomposition into a sparse component and a low rank component. Now suppose I can magically perform this separation. Then something extraordinary occurs, which is I can reconstruct part of the graph even though I don't get to see it. Right? So if I could somehow perform this separation, then I can infer something about a graph that I cannot even observe, which is quite remarkable. Okay, so there are many applications of this low rank plus sparse decomposition. There are applications in face recognition, in system identification, in quantum tomography, many fields, others than those we've talked about. So I'm going to try to spend maybe I'm going to spend some time on the theory of this, and then sometimes I'm going to show you some movies and applications and stuff. Okay, so, all right, so we've got this very tough problem to solve, where we have, as a statistician, we see the sum of a low-rank component and a sparse component. And I want to emphasize that I have known nothing about the low-rank component, L0. I don't know its rank, I don't know anything about it. And I don't know anything about what I'm going to call the corruption, S0. I don't know how many entries have been tampered with. I don't know where they might be. I don't know the magnitude of the corruption. I know nothing. Okay? And so what we're going to do is, well, we're going to use the simplest method that I know of to actually decompose this thing. And the program, the thing we propose, the way we suggest doing it is very, very simple. I'm going to try to find a fit L and a fit S, such that their sum is, of course, what I've seen. And among all these possible decomposition, I'm going to try to find one with minimum complexity. So what is a complexity in this world? I'm going to try to minimize the nuclear norm of the low-rank component plus a scalar, lambda, times the one norm of the sparse component. So maybe there are things, objects, so I need to tell you what are these objects. The nuclear norm is simply the sum of the singular values of the matrix L. Okay, so it's really like a matrix norm. Is I compute its spectrum and I sum it up. And that's a norm. And the one norm, I abuse notation, the one norm is what we use when we do the lasso in statistics, in sparse regression. It's like, the one norm is I just look at S as a gigantic vector and I just sum the absolute values. So the proposal has an extreme naivete. And the naivete is to say that maybe we will do well by trying to just, among all possible decomposition, find one that minimizes the nuclear norm plus a scalar times the one norm of S. Okay. And I have to say that this was proposed also by Chandrasekhar, Shangavi, Perillo, and Wolski from MIT. Okay. Any questions about this? This is a convex program, something you can solve very quickly on the computer. And in fact, I'll show you a demo of how it's solved on the computer. But this is a convex program, right? We have a sum of two norms. It's a convex objective subject to linear equality constraints. This is really a very nice thing to look at, computationally speaking. Now, basically, my talk is about this following phenomenon, which is bizarre. That you solve this optimization program, and what the program spits out, it spits an estimated low-rank component, which is exact. It's exactly L0. And it spit out an estimated corruption matrix, which is exact too. All right? So this is very bizarre. You make a low-rank matrix, you corrupt it by messing up lots of entries, and it doesn't matter. This stuff will exactly recover. It's a bit bizarre. Okay, but it doesn't hold always. It holds under broad condition. I'm going to try to explain what these conditions might be. Okay. So first of all, for such a stuff to be true, I claim that, well, the low-rank component cannot be sparse. So here I've got a matrix L, suppose you observe a matrix like this. Right? So it's a matrix that has one row of stuff, and then everything else is 0. And then I go to Victor and ask Victor, well, what is the lowering component and the sparse component of this matrix? And Victor gets back and he says, Emmanuel, your question makes no sense, because your matrix is both lowering and sparse. So I can declare that the lowering component is this and the sparse component is 0, or that the lowering component is 0 and the sparse component is this. I mean, what do you want? I mean, your question makes no sense. Okay? All right, so, and that would be right. So the lowering component cannot be sparse, and for the same reason, of course, the sparse component cannot be lowering for exactly the same reason. Right? Because in these cases, this question I'm asking, this separation question, makes no sense. It's like, it would be like in statistics when your signal looks like noise and your noise looks like signal. Well, try to separate them. It just makes no sense. All right, so the lowering component cannot be sparse. So if I've got a lowering component that looks like this, and I start to corrupt it, and here is what I mean by corrupting it. I'm going to take some entries and I'm going to corrupt them. Well, suppose I corrupt these entries. Suppose, in fact, these two rows were the same, exactly the same. And I corrupt the third entry of each row. How would you ever know what it could be? It cannot be decided what it can be. So let me give you an example, for example. Suppose that these are Emmanuel's preferences for movies, and suppose that these are Victor's preferences for movies, and let's say we're exactly the same. But let's also say that not only we're exactly the same, but the rest of you like nothing. There's nothing you like. So if you like nothing, you put zeros to everything else. So Victor and I were very singular. Right? We have preferences that are completely orthogonal to yours. And now, a demon goes and says, this was a godfather, erased my preference, erase Victor's preference, like input garbage. What can I do? I don't know. Okay? And so if the lowering component is like this, then it cannot be recovered. So what I'm trying to say here is that the lowering component cannot be sparse. What you cannot have is you cannot have rows or columns of your data matrix that are completely orthogonal to the rest. It cannot be. Because if rows and columns are completely orthogonal to the rest, even if you knew which entries had been corrupted, how would you correct it? Like you could not. Right? So suppose here we have a user and he's actually rating movies at random by tossing a coin. So he's unlike everybody else because he's just tossing a coin. Suppose that these entries have not been corrupted. I even tell you, you're missing this entry. What is it? Well, how can you predict the coin toss? You can't. Right? But if we're not, why is it that somehow the problem I'm trying to address is possible? Is because if users tend to be similar to each other, okay? So if the lowering component is not sparse, if we have similar users, well, there are many people like me in the population, and for those I have reliable ratings, so I can impute what people like me think about the Godfather, and that's why maybe it's possible. Okay. So to kind of quantify this thing, we introduced the notion of coherence. And the coherence is very simple. It says that we can see that if the singular vector, if the principal components, if you will, were very sparse, and here they would be very sparse because they would be supported on the first two basis vectors. If the principal components were very sparse, your kind of problem would be very hard to do. And so we're going to try to measure this geometrically. And geometrically, we've got this lowering component. And this lowering component has a column space and a row space. Right? So we can look at it through its SVD, U sigma V transpose. And what we're going to do is we're going to just measure the correlation of the column space and the row space with the basis vectors. Right? So this is what this condition does. We take a basis vector and we project it onto the column space. Right? And what I'm trying to say is if the projection onto the column space is very, very large, then I'm in a situation like this. If it's not large, then it means that, you know, I have groups of individuals that I don't have singular individuals, if you will. I don't have singular rows or singular columns. And so I might be in a favorable situation. So roughly speaking, the condition is there's a parameter mu that controls the correlation between the basis vectors, the coordinate axis, if you will, and the column space and the row space. Okay, and so we have two extreme cases. We have the extreme case where the column space contains one of the coordinate axes, in which case mu is very large, is equal to n over r. But for a random subspace, mu will actually be very low. It will be of roughly 1. So this coherence parameter is always greater than 1. It's between 1 and n over r. And we're interested in the case where mu is not large, so close to 1, not close to n over r. So mu is always between, where r is the rank of the low rank component. And so what I tried to argue is that if mu were close to this thing, then, well, we're in a very tough situation, where if mu is low, then maybe the coordinate, the column space and the row space, I don't have a matrix that can be both low rank and sparse when mu is low. It's not possible. Okay. Now finally, I mentioned that the sparse components cannot be low rank, and that's obvious, because if I'll give you the nicest matrix that is low rank, so I repeat the same rows many, many times. It's a simple low rank matrix I can think of. And now the daemon is actually corrupting all of these entries and puts stuff. How can I know what is x1? I will never know what it is. So if the daemon can actually touch entries in a very adversarial fashion, by completely removing a column, for example, I will never know where it's coming from. And so to kind of avoid discussing useless stuff like this, we're going to assume that the sparsity pattern is random. So the game we're going to play, and that's where probability comes in, by the way, because the daemon can actually select a lot of entries to corrupt, but this is going to be selected at random, and once this random set is revealed, you can do anything you want. Okay. Okay, and that's kind of the result. The result is something like this. Is, well, I observe L0 plus S0, this sum of a low-rank component and a sparse component. Again, I know nothing about it, and I'm going to do something a bit very bizarre again. I'm going to minimize the nuclear norm of the low-rank component plus 1 over square root of the dimension times the 1 norm of S. Like lambda is 1 over square root of dimension. Okay? I don't search for it by cross-validation. I just set it to 1 over square root of dimension. Okay, so I said, so now the rank can be quite large. The rank of the low-rank component can be essentially n over a log factor, so quite large rank. The corruption, I can corrupt a positive fraction of entries. Right, so every entry has a positive chance of being corrupted. So let's say 10%, let's say. And I'm going to solve this optimization problem with lambda equals 1 over square root of n. So what I'm solving is very, very simple. I just minimize. I mean, it's just ridiculous almost. So I minimize the nuclear norm of L plus 1 over square root of n over the 1 norm of x subject to L plus S equals. That's it. All right, and so with the result, which is a bit unexpected, is that with large probability, and so the probability of failure is 1 over n to some large power, at 1 over n to the 10 if you want, probability. I use probability because remember that there is something stochastic about what I'm doing, that the location of the entries have been chosen at random. Then there's this bizarre result, that this optimization problem, the solution to this, is exactly L naught, and n hat is equal to S naught. Okay, so let me just remind you of what this is saying. It says you prepare a low-rank matrix, whose principal components are not sparse, let's say. Then you go out and you corrupt lots of entries in this stuff, and you give to me the sum, and me in my laptop I solve this, and I will see exactly where you've corrupted the matrix and how. Okay. So it's completely exact. There is no tuning parameter, and it works always under associated assumption. Okay, so this is, well, maybe I'm not going to talk about matrix completion, which is what we were doing earlier, where instead of having corruptions, you've got just missing entries. So in matrix completion, which is kind of came before this, historically, the problem was not that you had corruptions, that you were not seeing stuff. Here we're looking at a problem which is harder. In the matrix completion case, you have missing entries. So any time you see a data point, it's a good data point. So you can use it for fitting and predict the entries you've not seen. In the robust PCA world, it's much harder. And the reason it's much harder is instead of missing entries, you have corruptions. And when you look at a data entry, you never know whether it's good or bad. And so you have to actually find out whether it's good or bad. It's much harder. It's much harder mathematically and information theoretically. Okay, so now there is something strange that I don't know if you've seen this in your own research lately, but there's something strange. Like what we're going to do is we're going to run this algorithm, just minimize the nuclear norm plus 1 over square root of n times the 1 norm. And we're going to run it on random problems. So we're going to make a random low rank and a random corruption and so on. And we're going to run the algorithm many times. And when you see a white pixel, okay, so on the x-axis, sorry, we have the rank of the low rank component divided by n. So if we're here, it means that the rank is n over 10. If it's here, it's n over 5. And here, it's n over 2. And on this here, we see the fraction of corrupted entries. So here means that I corrupted 20% of the entries, 30% of the entries, and so on. And for all these parameters, we're going to compute, we're going to run the algorithm, and we're going to see whether we get it right or not. And what you see is if you get it right always, you get a white pixel on this figure. If you get it wrong always, you get a dark pixel, a black pixel. And if you get it half the time, and half the time you fail, you get a gray pixel. And here you see no gray pixel. Either it works or it doesn't. And there is kind of what I want to call a phase transition between an area where it always works and an area where it always fails. And there's a boundary that explains very clearly the limits of the performance of this algorithm. So what does it say? Concretely, it says that at least on this random problem, if I have a matrix of rank n over 10, which is a rank enormous, like Netflix, you know, the rank that is being used in Netflix is effectively 50 out of 20,000. But say the rank is n over 10, then what this means is I can corrupt 24% or 25% of the entry and nothing bad happens. And if the rank was n over 20, I can corrupt 40% of the entry and nothing bad occurs. This is the same figure. If instead of corruptions, I delete entries, I don't reveal entries. And what we see is the size of the white region is largely extended because it's easier to impute than to correct and impute. Okay. Right, but what this is interesting is like, if 20% of the data are corrupted, it means like, okay, as long as the rank is like, n over 12 or so, n over 8, I'm still fine. Okay, so there's been a lot of other theoretical studies of this problem, a deterministic study by the work of these people that I've just mentioned before, and then it's a very big area of research now. There's lots of papers published about this, and they're great papers, and I don't have time to kind of discuss them in details. All right, so now you'd say, well, what if I have both corruptions and missing values? Well, you do exactly the same. That is, you just minimize the same functional, subject to, well, you're going to enforce the fit whenever you have data. That's the only difference, just exactly the same. And the theorem is exactly the same. It says, I have a low rank matrix. Let's say that 90% of the entries are missing, and of this 10% I get to see, well, the positive fraction is corrupted. Solve this optimization problem with now lambda, which is 1 over square root of the fraction of missing observed entry times dimension. Then the outcome is that. Right? So you can, if I give you a largely incomplete matrix of corrupted entries that has low rank, then you can compute. Okay. So you can correct and impute simultaneously. Okay. It's the same. Okay, so this is I mean, I know this is also a department of probability, so it's like to prove these things actually, I mean, I find it tough. It's a very difficult probability theory. It uses a lot of stuff. It's really, I don't know, if you know the book by Ledoux-Talleyrand, there's a lot of stuff from the book that goes in there. So it's not easy. But I want to single out a fantastic contribution by David Gross, who's a quantum physicist, who kind of looked at matrix completion, and we had the first proofs, and he was able to simplify them by using very clever insights and this new theory using this theory insights. Okay. All right, so now you'd say, well, but in reality, I don't have a matrix which is low rank plus sparse, right? So my matrix is not exactly low rank, it's approximately low rank, so I have a small perturbation, just like in classical PCA, plus corruptions. Right, so I'm low rank plus sparse plus small noise, because I'm not exactly low rank, I'm approximately low rank. You say, well, can you deal with this? And the answer is yes, because this extends to this case, and a lot of different things. So you can, once you understand the set decomposition problem, you can make it practically relevant because you can deal with really like what you'll see in practice, which is approximately low rank plus corruption. Okay, all right, so the question is, so we live in this big data world, and now you need to be able to solve this rapidly. And for those of you who know convex optimization, this can be formulated as a semi-definite program, but you should not try to use an off-the-shelf semi-definite programming solver, because the only size you'll be able to tackle is n equals 80 to 100. We want to deal with 20,000, hundreds of thousands of rows and columns. So we have developed a method that uses the methods of ADMM, of alternating direction method of multipliers, that I don't have the time to review. So I just thought that as a little trade-off, I will show you a little Matlab implementation. So I know I should use R, but I do my coding in Matlab, and I apologize for this, but I hope that the code will be transparent enough so that okay. Okay, so what I'm going to do here is I'm going to make a matrix M, which is 1,000 by 1,000. So it's going to have 1,000,000 entries. And the way I'm going to do this is I'm going to make a low-rank component by multiplying two random factors, one which is 1,000 by 45 and the other 45 by 1,000. So the low-rank component is a random low-rank matrix of rank 45. Right? That's what this does. And then I'm going to take 100,000 entries. Right? So the number of corruption n is going to be 100,000. So I have 1,000,000 entries, and I'm going to mess up 100,000. Right? So I'm going to take a random sample of size 100,000 among 1,000,000. S0 is a zero matrix, except on these random locations, I'm going to mess it up. I'm going to put stuff, and then I'm going to add them up. I'm going to show you the sum. Okay, so we've just done this. And now we solve this thing that is on the board. And so the only argument I'm going to pass is m, because lambda is 1 over square root of n. There's nothing I need to know. Just minimize this with lambda equals 1 over square root of n. That's all. Okay. So it's an iterative algorithm. And each iteration tries to guess. And you can see that, well, at least on this laptop, it's a MacBook Air, it's not a really powerful beast. After 16 iterations, or 6.8 seconds, it finds an answer. It finds an L hat and an S hat. And the question is, well, how good is it? Right? So, well, it seems to be pretty good, because the rank of the original L0 was 45, the recovering is 45, and the relative error between the two is 10 to the minus 6. That is, I got L0 to 6 digits of accuracy. And of course, if I got L0 right, I'm going to get S0 right, because just by subtraction. And so the cardinality of the corruption was 100,000. The recovered cardinality is 100,000. And I can get this. I can solve a problem with 1,000,000 variables in about 6-7 seconds on this laptop. Okay, now the thing that is a bit puzzling, and maybe I won't show you this, is like suppose now I take S naught, and I divide it by 100. So the corruption is 100 times smaller now. You'd say, Emmanuel, surely you're going to need to rebalance your lambda, like the noise level has changed. And absolutely not. Right, so I can make the noise level, and the reason I do it this is my wife, she's also a statistician, and she says, well, you know, you really need to create a tough problem, otherwise I won't believe you. And this, by scaling S, what that is here you see the histogram of the entries of S. So of course a lot of zeros and then some corruptions. And here you see the histogram of the entries of M, of the low-rank component. You see that the size of the corruption is completely in the bulk of the values of L. So by just looking at a large entry, you cannot decide that it's been corrupted. Right? And then we can resolve the same problem in exactly the same way. And maybe I won't bore you with the details, but it's going to run. And after like 30 seconds, you're going to find that you got it right, even though I did not change anything. Okay, so maybe I'll skip this and I'll come back to our presentation. Okay, so there's kind of a bit of interest in these things now. And if you look at Microsoft, they're actually implementing this on their high-performance clusters. And they do image analysis with this and stuff. Okay. So I want to show you some applications. I want to go back to so my last few slides are very just movies. So let's remember this is my detection problem where I want to separate the foreground from the background. I'm going to think about it very naively. I'm going to think about this as, you know, I'm going to stack the image sequence as column of a matrix, and I'm just going to perform this low rank plus sparse separation. That's it. And hopefully the low rank is a background, and the sparse component is a foreground. And when you do something like this, that's exactly what you see. So here you see the sum of the matrices, right? So this is a column of M, this is another column of M, this is another column of M. This is the corresponding column of L. This is a corresponding column of L. This is a corresponding column, and this is a corresponding column of S. And well, that looks like background to me, except that there's this person sitting in the background. And you say, well, are you sure it's background? Well, over the course of the video sequence, this person stood exactly still. So as far as I'm concerned, it's a statue. That's background. Now he sees a kind of the state-of-the-art method, which is quite complicated. It's going to be quite confused about what is background and foreground. But here's an example which is more interesting, because now we've got a scene in the lobby of a hotel. We have this person walk in. You see that the number of lights being turned on. So maybe, can I turn on this big light so that people can see the images better? Right, so you've got this, we want to do the reverse, I think. Yeah, exactly, that's better. So you see the illumination is changing. Okay. And the change of illumination is actually causing the kind of the state-of-the-art method to do not well, so being a bit confused about what is low rank. And well, this method works well and just picks up the person when you need to pick it up. And I think I find this extremely disturbing, because it's a non-parametric method. You just look for low rank and sparsity, and that's it. There's no model, nothing. And it's competing with state-of-the-art method. And that I find disturbing. So I want to show you some movies that are kind of fun. So this is a movie that I've not made myself. I've done movies like this. So we have a website where you can see lots of things like this. This is a movie by another team that does the same thing, separation of low rank plus sparse component. So you're going to see the real video sequence, the low rank component, the sparse component, the difference, the noise. Right, so this is with this extra little noise term. Okay, so when you do like this, okay, so these are people, this is just the low rank component, the sparse components, you see these people moving, and then the noise. Okay, very, very disturbing. But it can work so well with no tuning, nothing, out of the box. You know, it's bizarre. Another team from Singapore this time. So you're going to see the original video is in here, the low rank component is here, and this guy is going to turn the light, so there's a sudden change, but it doesn't matter. The L and S component automatically adapt to this. Right, so again, so this guy walks, that the original, that your M, that the low rank component has been completely erased, as you can see, and because he's in the S component. And so, so you've got things like that. Yes, of course, this is a perfect method to remove impulsive noise. Here you have a very noisy video. You model this as a low rank plus sparse component, and it cleans up immediately. Okay, right, that works good. It's just no tuning. Just throw the stuff at the software, and you don't try to understand anything, and that's what it does. Which is why it's disturbing. Now, in the interest of time, there are lots of communities that become to be interested in this, especially people in MR. And it's a bit outside of what I wanted to discuss today, but if there is interest in this, so the low rank plus sparse model is used to actually enhance MR sequences, dynamic MR sequences at the moment. And I have the good fortune of working with Ricardo Tasso and Daniel Sodikson from NYU, who are both radiologists. And so we use this model to extract much sharper and far better video sequences of your heart beating and stuff like this, using these ideas. Like one of the things that people are trying to do, okay, so maybe if there is interest in the end, I will say more about this if people are interested. But what I'm trying to say here is you can do more than. Okay. So this is the kind of stuff we've seen. Is of course you can, in fact, if you go on the web, you'll see a lot of L plus S models to actually denoise old movies. So here's an old movie where you have speckles. I'm sure you've seen this. And so of course it will show up in the sparse component, so the low rank component is clean. Stuff like this are completely erased by this method. You have these lines that are gone. There's these lines that disappear here. These lines that are gone, all these speckles are gone, etc. Now, of course, you would not want to have Tom Cruise disappear, so you have to maybe do some tuning a bit right. But okay. All right. Okay, maybe I'll show you some fun things now, and this is not my work. So it's of course motivated by. Now you're going to see stuff that is broadly motivated by face recognition. So face recognition is a tough problem because of the non-idealities that I mentioned before. Now, if I had people that were aligned in front of me on a white background and under various elimination conditions, all of this would work. The problem is that when you have real images, they are not like this. People will turn their head, they will be misaligned, and so on and so forth. So you don't have this low rank plus sparse structure because people are misaligned. So the idea of Emma and his colleagues from Microsoft is to say, well, is it not possible to find a deformation, a very simple parametric deformation of your image sequence, such that after deformation, you get the low rank plus sparse structure you're looking for? And so you just do it the way you think you should do it, is that you try to say, after deformation, I want to be as low rank plus sparse as possible, so I want to minimize this. And so now we look for L, S, and tau, the deformation that makes the thing as low rank and sparse as possible. Now this is not a convex problem, so, well, but it doesn't prevent from trying. So this is quite extraordinary because suppose that you've got pictures of this. So you're looking at a facade of a building, but from different point of views. Like let's say you have a car moving and you make pictures like this. Clearly, if I could register this image, I would have low rank plus sparse. Right? And the tree is a sparse structure occluding this kind of same thing, which is my low rank thing. Now, when you try to use this method by trying to make the thing after deformation as low rank plus sparse as possible, well, what this method does is it will rectify these images to look like this, so that then there is a low rank component and a sparse component. So you completely separate these two things. So this is really extreme because suppose I give you a database of faces like this, and some faces have been tilted, and the eyes are occluded. I don't know if you see these occlusions everywhere. They've been occluded, they're being rotated. And then you apply this low-rank plus sparse structure after deformation, here after rotation. And what you get is you get the aligned set, still corrupted by this occlusion, the low-rank component where these occlusions have been removed, and of course they will show up in the sparse component down below. So in this our area, here's the most fascinating experiment I've ever seen. And I actually met this guy, so I think it's true. Because it looks eerie to me. But here are 40 photographs of a guy whose face you'd like to recognize under extreme diverse conditions. So here's wearing sunglasses, here he decided to wear a wig, here he has a hat, he has these strong shadows obviously, a hand in front, he's shouting, here the mouth is closed and so on. And now you go through this low-rank plus sparse deformation. And this is the corresponding columns of your matrix. So each image is a column of M. And here you see the column of the low rank and the column of the sparse error. So it's called A and E in this case. But let's look at this guy. So this guy, here's the corresponding column. So you've removed the sunglasses and you put the eye instead. And here, like, it was just below. You had, like, the mouth was covered, and now you just do this. And here you had the hat, which is this image, and you removed it, and you put the forehead the way it used to be. It should be. And of course, all these non-idealities will actually show up in the sparse component. So the hand will show here, and so on. And now, let's say you pre-process data like this, and say, is it going to be hard to recognize? It's going to be hard to recognize this guy because he's wearing sunglasses. But now this guy is this, so is it easy? Well, yeah, maybe it is easy. Okay, so these are average faces of people before alignment and this repairing by low-rank stuff. So you see famous people, I don't know if you recognize some I think you can see who they are. And some it's a bit harder. But suppose you do this alignment and then you just average the low-rank component. What do you get? These are data retrieved from the World Wide Web. So all of a sudden it comes into focus. It's kind of not easy, who is this guy? But I think it's pretty clear now. Okay. All right. Okay. Now, so what I'm trying to say is that this might be a useful processing technique to do classification and all kind of recognition, because, right, so for example, what I've learned as a grad student is hand-digit recognition is hard. It's hard because people write the number 3 many, many different ways. Okay. But suppose you apply this low-rank plus sparse decomposition. So what this does, it rectifies the number 3 so that after rectification, it is as low-rank plus sparse as possible. And so this 3, which was a bit bizarre and would be tough to recognize, is now this 3, and it's much easier. Okay, so. All right, so people do lots of stuff with this in all areas of computer vision, but maybe this is not your area of interest, and maybe I won't talk to you about it too much, but like, what is cool? Like, you can take stuff like this and apply essentially this technique to rectify, to actually guess the geometry of objects. Right, so one of the things people try to do is they try to extract 3D from 2D. Well, so basically you can try to use these techniques to actually guess the orientation of objects in space by rectifying them so they appear as low-rank plus sparse as possible. And so that works well, and then people, if you take a picture like this, it will rectify it this way, and text will be rectified. And so you actually learn the 3D geometry of things just by stuff like this. So you can rectify all kinds of stuff like this, and even things like this. Okay, so the work of E is interesting because it's using its kind of low-rank plus sparse recomposition to actually recover 3D structure from pair of images. Okay, so I'm running out of time, so I'll just thank you for your attention, say that I presented a principal approach to robust PCA that works well in theory and in practice. There's a lot of work in my community trying to kind of design good algorithms for fitting this stuff. because people recognize that there are quite a few applications. And so if you're interested in learning more, we published with my colleagues, but now a paper in the Journal of the ACM. But now there are many, many papers on this topic, and it's a very active research, and I have by no means the last word. Thank you.